This recording is for the Unit 2 class live on application of conics. So it talks a couple things about variation which do apply with conics. We have varies inversely. And what that means is that as one variable goes up, the other one goes down. So the way we would express that is y equals k over x. So y and x, of course, are the two variables that we're talking about, and k is the constant of variation. So that means that they are changing no matter what numbers we plug in for x and y. They are always changing with that same amount of k. So, for example, if we're looking at a horizontal beam and the amount of pounds that it can hold safely, they would give you some sort of scenario and say y equals the safe load in pounds, and x equals the length in feet, of the horizontal beam. So a couple things, then they'll give you some information about this scenario. So they've defined those variables for you, which makes it much easier, but they might say determine the constant k if y is 2,000 pounds and x is 15 feet. So what we do is we plug it into that formula, the y equals k over x, and so we have 2,000 equals k over 15, and now it's just an equation that we need to solve for k. So we multiply by 15 since it was divided, times 2,000 times 15, and then so 15 times the 2,000, and we get k is 30,000. So no matter what numbers that we plug in, we always know that in this scenario that y and x are going to be varied by 30,000 regardless. Okay, so what that means is in this situation we would always have this equation. So if they asked further and said, well, now that we know the constant that this is working, what is the safe load if the beam is 10 feet? So we know that it told us that the beam was x, and so we would have y equals 30,000 divided by 10, so y would equal 3,000 pounds. So the reason for this is it allows the situation, to look at the variables and how they are interacting with each other, and then be able to just plug in numbers if I have different beams or different loads that I have to calculate. It makes it much faster. You can also have direct variation. And direct variation looks like this in its basic form. And so this means that another thing is that these variables, if one goes down, the other goes down. So, in this case, let's look at an example that uses direct variation. And again, it could have some modifications. So this one will have the modifications. So y equals the safe load in pounds. And x equals the depth in inches of the rectangular horizontal beam. So this one is going to use y equals kx squared. And yes, they will give this to you. So notice the x is squared. So let's look at a scenario that uses this. So they may again say find k if y is 1,000 pounds and x is 5 inches. So we would have the y equals kx squared that they gave us, and now we plug in those numbers. So 1,000 equals k times 5 squared. So 5 squared is 25. And then to get k by itself in this case, we need to divide by 25. And so then we figure out 1,000 divided by 25 is 40. So this one is y equals 40x squared. And then to add to it, now that we know that, we could then answer questions like what depth should support um, 16,000 pounds. So we plug that in. So we have y equals, 40x squared. And so we have 16,000 pounds equals 40x squared. Then we divide by 40. And so that gives us 400. And then how we undo a square root is that, or undo a square is a square root, rather. And so we get x equals 20 inches. Alright, another example. So Galileo investigated the relationship between the distance a ball rolls down an inclined plane and the time it takes to travel that distance. So here's what he came up with. He looked at the time that it took, so that's our x, and then how far it went, and so that's y. And so they give you a chart to look at. So here are the charts. So, he looked at the time and he got 1, and then the distance was 33. 2, it was 130. 3, it was 298. 4, it was 526. 5, it was 824. 6, it's 1192. And 7 is 1620. Now, here's the question behind this. What conic section fits this data? So we have to think of the conic sections. You know, there's circle, ellipse, hyperbola, and parabola. And so what we do is we take this data and we actually graph it. So we want to get some graph paper and plot that and see what it looks like. So in short, here's what happens with that. It looks like this. So when I look at this, it doesn't really look like any of my conic sections necessarily, but if I look a little further and read into it, it looks like half of a parabola. So in this case, it's a parabola. Now we know that parabolas are the equation. The easiest, simplest, basic graph of a parabola is y equals x squared. So this is what we're going to know and use for the second part. So they may say use the point 133 to determine the constant like a constant of variation, and then write the equation. So we know that we can take that parabola equation and know that it could have a number in front of the x squared. And that's exactly what we're looking for. So now we can see the relationship between this and when they were talking about variation. So I know that this point is and y. So I'm going to plug them in. So 33 equals k times 1 squared. 1 squared is 1, 1 times k is k, so k is 33. So the equation that we need to write is y equals 33x squared. So that's the end of this recording. Now you need to call, text, or Skype message me so we can talk about this recording and you can get credit for it. And so have a great day.